we would like to determine whether the following series converges. And the first thing we can think of as a way to make progress for this problem is to assume that it converges and see where it would converge to. Now, there is a theorem which precisely describes how this would take place. This is the theorem, and it talks about the sum of terms, and you have a multiplying factor, and this is the eventual formula. Now, under the assumption that it converges, this means that the absolute value is less than 1. The absolute value of the ratio is less than 1. So perhaps we would like to combine these two objects, the theorem and the series, and try to make something out of it. The goal eventually, if we assume that it is convergent, is to find this multiplying factor. In this sum, this might not be obvious at first glance, but perhaps you could try to figure it out after you pause the video. Think about it. Immediately we notice that there is a mismatch in the exponent. Here the exponent is k minus 1, and there the exponent is k. I think it would be nice if we had everything under one exponent. So if I work on this term alone on itself, I could effectively, and I would like to write it as 4 to the k minus 1 minus 3 to the k minus 1. Because if I do this, I can take the k minus 1 and write it down like this. Of course, I could also write it as minus 3 to the k. These are just technicalities. Eventually, you should be able to reach the same conclusion. In any way, notice that what we've done here is we've took away 1k, but we can't just do that from, we don't have this freedom. So if we take away 1 in the exponent, we have to add 1 in the exponent. And adding 1 in the exponent gives you a quarter. So in other words, 4 to the k is equal to 4 to the k minus 1 times 4. This is all happening in the denominator. And I take the 4 to the k minus 1 in the denominator and I combine it with the numerator to get this expression. So this seems like a good way to move forward. All right. This is all happening within itself. I would like to write this quarter, bring it outside of the sum, and then I would write 1/4 of infinite sum from k is equal to 1 of this expression. I think that's fine. I hope you don't mind this. And since the index is starting from 1 and we have k minus 1 and it's an infinite sum, so the indices run infinitely often over all of the numbers, then it should be okay if I write this as 1/4 of the sum from k is equal to 0 to infinity of minus 3 over 4 to the k. And this is completely fine because if you will let me draw your attention to the first few terms that would come out of this both infinite series, and I will ignore the 1/4 for the time being. Okay, maybe I will not ignore it, but the first term will be minus 3 over 4 to the power of 0. Second term will be, if I plug in k is equal to 2, I'll get minus 3 over 4 to the power of 1. There, I will get 1/4 on the outside, and I will get the exact same thing. So minus 3 over 4 to the power of 0, and then minus 3 over 4 to the power of 1. I could do this infinitely many often, but I don't think we have infinitely many time. So you have to trust me that it goes on like this. Now I'll remove this since this is more of an illustrative thing, and it is not practical to have it written down. But then it is good, because if this is what we have, then we have effectively found our x lying around here. And to our good fortune, the absolute value of this x is less than 1. I mean, there's nothing bad about being divergent. It doesn't make you a second-class series in the sense. There's nothing wrong with divergent series, but it is convergent. Maybe I'll stop now. I'm not too political when it comes to geometric series. So I need to work on that. But anyway, so we would like to now utilize this theorem, and so the quarter is on the outside. Now for the sum itself, I can replace the sum by 1 over 1 minus the multiplying factor, which is minus 3 over 4. Now don't be tricked by the minus. There's already a minus, so these are two minuses, and that is what we get. 1 over 1 plus 3/4. This will give you some number. I think it will be 1 over 7, because this gives you 7 over 4, and it's in the denominator, so you flip it, you get 4 over 7, and the 4 cancels out with the 4, you get the 7. But I could be wrong. This doesn't have to be correct. But what I am 100% sure about, and 100% sure that is correct, is this expression here. And from there, there's not much you can do to reach the end of this solution. For this type of problem, we should always think of the geometric series formula, the infinite geometric series formula, and you have to make sure that your multiplying factor is less than 1 by modulus, because if it is greater than 1 by modulus, then your series, in a sense, is increasing and increasing and increasing in magnitude, perhaps, with reference to the biggest, the next term in the series. And from there, it doesn't look like it will converge, and it doesn't converge. Perhaps it converges to infinity or minus infinity. But that, by definition, is divergence. So let us not diverge too much on the topic and end things here.